Welcome to the lecture on independence and homogeneity using a chi-squared distribution. So to begin, we're going to talk about the tests of independence. Tests of independence involve using a contingency table of observed data values. And the way that we're going to compute our test statistic is going to be from observed minus expected squared divided by the expected. Those are our residuals. And then we're going to add them up for each position in this contingency table. That will give us our chi-squared test statistic. So O stands for observed. E expected. I is going to be the number of rows. J is the number of columns. And since we're using a chi-squared distribution, we'll need to know degrees of freedom. So that's going to come from 1 less than the number of rows times 1 less than the number of columns. From observed values, we'll have to compute expected values. And because we're doing a test of independence, we're going to rely on the definition of independence. In particular, if we have two events, A and B, then what it means for them to be independent is simply that the probability of A and B both occurring is equal to the probability of A times the probability of B, right? This is our definition of independence from our basic probability unit. And in words, what it means, A and B, looking at our definition of events is that we get a person gets a speeding violation in the last year and that they're also a cell phone user while they drive. So let's do an example on how to compute our expected values using the definition of independence. So we're given some information here, a study of drivers who received speeding violations in the last year and who use cell phones while driving. There were 755 people in that study. So this is the total number of people in the study, hence it goes in our total of totals. This is everybody, 755. Out of the 755, 70 had a speeding violation. So if I look at the total for speeding violation, that's going to be people who use cell phones and who did not, but I'm not making that delineation yet. I'm just looking at how many people had a speeding violation, and that was 70. Similarly, 685 did not, so that's going to go here. And now I can do the same thing with cell phones and not cell phones. So 305 use cell phones. That goes in my total for B. And 450 did not. So this is our contingency table. We're well on our way. And what I want to do is I want to see if I can figure out these 4 values here. These would be my expected values based on the supposition that A and B are independent events. So remember that the probability of A and B, if they really are independent, should equal the probability of A times the probability of B. So the probability that A occurs is 70 out of 755, right? The total number of A's divided by the absolute total. And then for B, that's going to be the total number of B's, which is 305 over 755. And the probability for A and B is going to be some number here, unknown presently, out of 755. So I can actually solve this. I'm going to multiply each side by 755. And I'll get a nice cancellation on the left, leaving me with just the number for A and B. And then I'm also going to get a good cancellation on the right as well with one of my 755s. So I just end up with 70 times 305 divided by 755. And if I put this on my calculator, I get approximately 28.28. And so in this way, I'm able to compute my expected value based on independence, right? Based on the assumption that A and B are independent, this should be 28.28. I can do this for every single value in the box. So for example, if I wanted to do did not use cell phones, but also had a speeding violation, namely if I wanted to do this guy here, then I would do the probability of A and not B. So this is going to be equal to whatever that value is, whatever that count is over 755. This should be the probability of A times the probability of not B. So this is going to give me, the probability of A is still 70 over 755. And now the probability of not B, instead of 305, is going to be 450. I know I can cancel out a 755 on each side. Excuse me. And you'll see this nice little pattern that we get here. Boom, 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 boom. Whatever number you're trying to get, you can see that it's just the total 70, the total 450, multiply those together and divide by 755. So this was 70 times 450 over 755, right? Your row total times your column total divided by the total. And so in that way, this would be 685 times 450 over 755. And this one would be 685 times 305 divided by 755. And so that's how you're getting your expected values using the idea of independence. So of course, the whole point of this is if we want to test for independence, we're going to have to compare these expected values computed as such versus a set of observed values, compute the residuals for each one, sum those residuals to get a chi-squared test statistic, and use that to compute a p-value, which will lead us to a decision for failure to reject or rejecting. So in summary, if speeding violations and cell phone usage while driving were independent, then you would expect to see the values in the table that we just did. If the observed data is very different, then we're going to have to reject the idea of independence. And just as in the goodness of fit test, we need to make sure that our expected values are at least 5 for every position in that table. Our null and alternative hypotheses are always going to be set up where our null hypothesis is that the factors are independent and the alternative is that factors are dependent or not independent. So if I look at this example, I'm looking at the number of hours that a volunteer group worked or volunteered versus what type of school they go to, what type of college they go to. And I want to know, are these things independent? Does the type of school that someone attends affect the likelihood of how many hours they're going to volunteer? So all I really need to do in order to compute this is I need to put this data into Excel. So when I'm putting this data into Excel, I want to make sure I'm on my independence and homogeneity tab. And I also want to make sure that I'm only putting in the data values. Like notice that I have columns on the bottom, I have totals on the bottom and totals on the right. So I don't want to enter the totals. I just want to put in the values. So 111, 96, and 91 for volunteering 1 to 3 hours. And hopefully my totals match 298, yes, and 298 in my given. So I'll fill out this entire table. With each cell that I fill out, I'm getting some output below it. And that output is exactly my expected values, which is what I want. So if I look at my expected values, in my first position, I have 111 people from community college volunteered 1 to 3 hours. My expected value was only 90.57. So in these gray boxes, these are my expected values, and I can compare them to my observed. And once I do that, we can talk about the residuals. So with my recorded expected values, I can go ahead and look at the residuals here. So in this far right section of the tab, we're given our outputs for our test statistic, our degrees of freedom, our p-value, and then we have a place to compare that to alpha. We're also given our chi-squared sums, and these are just our residuals. So by looking at, let's say, this position versus this position. So your residual is observed minus expected squared over expected. So for us in this first position, we have 111 observed. We expected 90.5721. So we look at that difference squared, and then we divide it by the expected value, which was 90.5721. So just to do one by hand to show, so I get 20.4279. That's how far off they were absolutely. I still need to square that and divide it by 90.5721, giving me 417.2991. Right, and so if we look at what's going on in Excel in that first position, 4.607, that's what we just computed by hand. So instead of having to do that for all 9 spaces, we're going to have Excel compute those, and those are the residuals. So once I have my residuals, I can add all of those up, and that's going to give me my test statistic. So with all my residuals computed, just taken over from Excel, if I add all 9 of these values, that's going to give me my test statistic here, 12.991. And with that test statistic, I'll use my chi-square distribution with 4 degrees of freedom, and I'll get a p-value of 0.0113. So then what's left is decision. So since p is less than alpha, I can reject the null hypothesis, which is rejecting that they're independent. And I have enough evidence to support that they are dependent. So the next test is going to go pretty much the same way. We're going to do a test of homogeneity, and this is just a test of sameness, meaning I want to test if 2 things are the same or not. So the test of homogeneity is also going to use a contingency table. We have the same sum of residuals with the same definitions for O, E, I, and J, observed, expected, number of rows, number of columns. The degree of freedom is computed in the exact same way. What's a little bit different now is that our null and alternative hypotheses have changed. So H naught is that the distributions of the two populations are the same. And our alternative hypothesis is that the distributions of the two populations are not the same. As before, we need to make sure our expected value for each cell should be at least 5. This is the same as also goodness of fit. So we want to test in this example whether male and female college students have the same distribution in their living arrangements. So here we're given our expected values, our observed values. And really this is just an observation. Really we're just testing to see if the observed values maintain the proportionality. So if we have 250 males and 300 females, we're going to expect to see a 5:6 ratio consistent across the categories. And the way that we're going to look at this is just throw it into Excel and see what kind of comes out. So let's do that and digest the output. So again, we want to be super careful that when we put our data in, we're not including the totals. We just want to include these values here. So having done that, we can also verify that our totals match 163, 170, 137, and 80 with a grand total of 550. And so now we can actually compare that. These are our observed values in pink. We can compare that to our expected count down here. So I'm going to transfer over our expected count and then we'll look at the residuals and decide. So what I mean to say by observing proportionality here, that's going to be the basis of how we're getting these expected values. So let's just look at one cell. We'll look here at this guy. Actually, the first column. So what's happening is in the first column, your total is 163. If we're preserving proportionality, then what we want or what is expected for the males is going to be 250 out of 550 times 163. And what's going to be expected from the females is going to be 300 out of 550 times that 163. And so if you were to actually crunch that out on your calculator, you would get the same answer that Excel produces, which is exactly what Excel is doing in order to get your expected values. So again, it's just a preservation of the proportionality on the two populations to say whether or not they're coming from the same distribution or coming from a different distribution. So that's how you would get the expected values. Now that we have them, we can compute the residuals. So it's the same thing that we did before in the test for independence. So if we look at, say, the first position here, comparing to the first position here. So our residual is going to be observed minus expected squared over expected. So our observed was 72, our expected was 74. So if we crunch that out, we'll have to be mindful to square the negative as well, giving us 4.3719. divided by 74,0909. Oops. And so that's our residual for that first position. And we would need to do it for all 8 positions. In particular, we would get these values here. And the idea is that those residuals would then lead us to our test statistic, 10.129. Simply by just adding them all up, right? So if we were to add all 8 of these values, we would get 10.129. And then from there, we would compute a p-value of 0.0175. And since p is less than alpha, we are going to reject the null hypothesis. We're going to reject the idea that they come from the same distribution. And that's the end of our hypothesis test for homogeneity.